Good afternoon to everyone. For those of you who don't know me, my name is Gabriele Guerrini, and I'm an assistant professor with the University of Pavia in Italy. Today's webinar will cover an important topic regarding masonry buildings, that is, how to improve connections between the structural elements of these kind of buildings in order to prevent or delay the development of local mechanisms. Now, probably you remember, if you followed the previous webinars of this series, you remember this slide. This is basically a summary of the framework for the assessment and retrofit of existing buildings according to Eurocode 8, Part 3. And in the previous sessions, we have talked about knowledge of the building, different methods and problems related to the analysis of these buildings. Now we are focusing on the last part, which is how to retrofit, how to strengthen these buildings. So, what are the typical failure modes of masonry buildings? Well, for poor construction, let's say in rural areas or mountain areas, typically we have very low quality materials. And in these cases, the problem that we often observe in earthquakes is the disaggregation of masonry, which is considered a local mechanism itself. If the materials, however, are good enough, then what we typically have found is that local overturning mechanisms develop. That is, walls tend to overturn out of their planes. And this is probably one of the most common sources of vulnerability of masonry buildings. And only if we have effective connections preventing the development of this mechanism, tying all the elements all together, only under this condition, we can develop a global response of the building where the walls, their piers, their spandrels respond in their planes, which is what we would like to happen because we can exploit most of the strength associated with the materials. Now, depending on how connected walls are among each other and with floor and roof diaphragms, we can develop different overturning local mechanisms. If we have poor connections with both intersecting walls and slabs, diaphragms in floors and roofs, then we may develop a simple overturning mechanism where a wall, usually a facade, detach from the other elements and tend to rotate out of its plane and fall down. However, if some of the connections with the roof or the floor diaphragms are sufficiently strong, then we may prevent this kind of overturning, and we may actually observe another mechanism, which is so-called vertical arching. On the other hand, if we don't have a good restraint at the top of the walls and with the slabs, but we have good connection with some of the intersecting walls, we may develop combined overturning mechanisms. Well, a facade is rotating and it's basically moving portions of the transverse walls in its mechanism. And finally, if we don't have good restraint at the top, but we have quite effective connections with the transverse walls, then we may observe the formation of an horizontal arching mechanism. These are only some of the possible mechanisms, the most common mechanisms related with overturning of the walls that we can observe, but other more complicated situations may arise. However, what we want to do is to prevent the development, or at least delay it, so that we can first activate the response of these walls in their planes. Why do we want so? Well, we know that the in-plane strength of walls is way higher than their out-of-plane strength. And so this is why we want to activate their in-plane response rather than their out-of-plane response. And in fact, they can brace the building much more effectively if they respond in their planes. But for this to happen, as we have seen, we need to tie together all the elements. We need effective connections between the intersecting walls and between floors and diaphragms. And we need to have these good effective connections as much as possible wherever we have intersections, in order to promote the so-called box type response of the building. So, first of all, we need that intersecting walls are well connected with each other. This will provide vertical restraint against out-of-plane overturning mechanisms. This may be achieved already by good detailing of the construction. This was sometimes done in the past with the use of large cornerstones that were providing quite good connection between the walls meeting at the corner or at the intersection in general. And if this happens, you see, we can avoid the mechanism of simple overturning when shown at the top left, and we can activate the one in the center, where the wall tries to rotate out of plane and is also involving in this rotation a wedge of the transverse wall. But we may want to do even better. So if we want to involve in this mechanism a larger portion of the intersecting wall, we may want to tie together these two perpendicular walls, tie them with each other. And to do so, we may, for example, introduce tie rods or other type of improved connections. Then, wall-to-diaphragm connections and their combination with sufficient diaphragm stiffness and strength will also provide horizontal restraint to these out-of-plane mechanisms. The tie rods that can be used for improving the connection between intersecting walls are also effective with this role, but they may not be sufficient, especially if the walls are long. So if the distance between the intersecting walls is high, because in this case, the central portion of the wall excited out of plane may not be restrained by the intersecting walls and by the tie rods, which are usually running close to or within the intersecting walls. To avoid the formation of the mechanism at the bottom center, where you see the edges are restrained, but we may develop horizontal arching. Well, to avoid this horizontal arching from happening, we need to take advantage of diaphragm stiffness, strength, and connection between the diaphragm and the walls. By doing this, we can restrain way more effectively the wall. And to do so, there are several options that we will see, but they mainly include connection between joists, between rafters, between beams and the walls, and also improvement of the connections within the diaphragm, within the floor members, and additional elements to increase their in-plane stiffness and strength of these diaphragms. The effectiveness of good and improved connections has been shown in many actual cases with real earthquakes. These photos were taken in Amatrice in Italy after the 2016 earthquake. We can see that the building pointed by the green arrow was equipped with tie rods, and it survived the earthquake pretty well. But the adjacent building, which most likely built with similar materials, similar construction methods, you see it's completely collapsed. And that building didn't have any tie rod, any other intervention aiming at improving the connections. So you can definitely see that in the same location, two adjacent buildings, the one with the effective connections resisted much better than the other one that collapsed entirely. Also, the statistics from actual earthquake confirm this observation. Here, what I'm showing are fragility curves for different situations. Buildings, you see the top row is for stone masonry, the bottom row is or brick and block masonry. And then we have on the left the cases of flexible diaphragms, on the right the case of rigid diaphragms. Now, each curve, each color is associated with a certain limit state. It could be serviceability limit states, green color, all the way to ultimate limit states with a red color. Basically, a steeper curves is associated with a higher risk. So already without any connection improvement, you can see that the effect of rigid diaphragms is making these curves less steep. So already having rigid diaphragms is helping reducing the risk for all limit states. But look at what happened for the cases with tie rods or tie beams, let's say with improved connections. Here you can see that all curves are lowering, they're all becoming less steep. So this is again proving the fact that we need to provide, to improve, to ensure this type of connection. Because again, most of the collapses that are observed in earthquake, but also most of the damage is associated with out-of-plane mechanism development. So how can we promote a box-type response? Well, in the previous sessions of the webinar series, probably in the first webinar, if I remember well, we already saw this slide. Basically, we have different techniques aiming at improving the connection between elements, between intersecting walls and between walls and diaphragms. And also, we have other methods for increasing the in-plane performance of our diaphragms. And a combination of these solutions is usually needed to improve the response of a building. Which of them to be implemented depend on the case that you are considering, depends on the specific vulnerability of the building that you are analyzing and possibly strengthening. Now, let's start from the connection between intersecting walls. If the construction details adopted at the time of construction are not sufficient to ensure a proper intersection, a proper connection between the two walls, then we may provide, for example, reinforced injections. Now, these techniques is basically consisting in stitches inserted within holes at the intersection. They should bridge eventual crack that would form for separation between the two walls with the overturning mechanism, and it will connect the wall which is overturning out of its plane to the one that is resisting in its plane. It can be provided at corners, it can be provided at interior intersections, and you see these photos were taken again in Amatrice after the 2016 earthquake. This building was heavily damaged. You see on the right-hand side, there is a heavy damage in the plane of the building, but you see, this is in-plane damage. And you can notice that we have all these with these columns of holes at the corners of the building that were patched. Why these patches? Because underneath we have these reinforced injections. You see, they were very, very effective at tying the building together in combination with tie rods at the top. The fact that the building was heavily damaged in its plane, okay, meant that this building had to be torn down after the earthquake. However, no one died in there, it didn't collapse, and it survived, even though heavily damaged, the earthquake. All the damage is in plane. You see all piers and all spandrels, in this case, are cracked in shear, which is actually somehow good, because it means that we were able to take advantage of all the strength of this element, the in-plane strength of this element. They were all exploited all the way to their end. And this is good news. It means that this type of interventions can actually be effective at promoting our desired box type behavior. However, we need to be careful on how we implement this kind of intervention. First of all, we may have problems with bond between the reinforcement, usually rebars, within the ejection. So it may be preferable to use inclined ties, inclined bars, to avoid problems related to debonding and then to ineffectiveness of the intervention. As you see here on the photos on the right-hand side of the slide, you see the wall of this facade just collapsed, but you see it was connected only at one location with a rod, with a single tie that basically pulled off the facade. Well, there was a problem of bond, but there was also another problem here. We had only one connection there. This type of intervention is effective if it is distributed throughout the height of the intersection, not like this. Here it was impossible to do anything at the bottom because you can see inside the building there were arches below. So in this case, the intervention was basically useless. It didn't prevent the overturning of that wall. So again, be careful when you adopt this kind of measures. Make sure that the way they can be implemented are actually effective. Otherwise, you are doing something that has no significant effect on the final performance of the building. If we need something more than improved intersections between walls, then we may add tie rods that are usually post-tension. That is, they're inserted, they're applied, and then they are pulled, reacting against a bearing plate on the walls, and then they are left in place with some tension inside. By doing this, we are basically pre-stressing, with the post-tensioning technique, the spandrels of the building. You see here a figure with a possible layout of tie rods. Ideally, they should be placed on both sides of the wall or in a horizontal hole all the way through the entire wall in the center in order to provide a more centered post-tension force. However, usually they are not applied except for very rare cases on the outside. They're only provided inside the building, and also for interior walls, not always on both sides of the wall. The need of this kind of connection was already known in the past. You see the photo here at the bottom left. You see this wood element. Well, that was actually a tie rod from the past. It was made of timber. At the end, there were connectors with bearing plates in order to fix it to the wall, to fasten it to the walls. So the idea is the same as the modern one with steel post-tension rods. And however, you can see here the detail of the connection can differ quite a bit. Usually, we recognize the presence of these tie rods from their anchor plates, because typically they're anchored mechanically. However, we may have cases where we cannot provide this mechanical anchorage. For example, if there are walls not aligned, or if the wall ends in another property which is not accessible, or problems like this. And for these situations, we may need to anchor the tie rod by bond, as shown on the left-hand side of the slide. On all other cases, we typically adopt bearing plates, which can be visible from outside, especially if the masonry is not plastered. But in case of plastered masonry, we may basically obtain a pocket on the external surface of the masonry and install the bearing plate inside the pocket to hide it from the view, if we don't want to see it for some aesthetical architectural reasons. The anchor system is a delicate part of this retrofit solution, because it needs to transfer quite high forces when an overturning mechanism tries to activate. So the bearing plate must be big enough to apply a pressure to the masonry which is not excessive for the masonry strength itself. And if the plate is wide, we may need to stiffen it with ribs in order to avoid problems of bending of the bearing plate itself. And in fact, you can see what may happen. Here on the left-hand side, we have a case where the tie rod on one hand pulled in the masonry. You see, in this case, the anchor system bent, basically, while the rod was pulling in. On the other side of the wall, you see the anchorage, which is extending outside. It's not bearing against the masonry anymore, because that rod is basically shifted all the way to one side, and it has completely lost its effectiveness. On these other photos, in the center of the slide, we can see failure of the masonry behind the anchor plate. Again, a problem of excessive bearing pressure. In this case, failure was on the masonry side rather than on the anchor system side. And finally, on the right-hand side of the slide, I'm showing you an important detail. Now, when you don't use wide bearing plate, but these other systems, which are narrow, be careful on the orientation of that anchor, because it needs to engage either the transverse wall or the slab. The situation at the bottom right is not acceptable, because in that case, you see only half of that anchor system is bearing against something. The other half, you see, is just pushing on a wall without anything to bear against. And that's not something that should be avoided in order to prevent problems with bearing and with anchorage of the tie rod. Then we need to consider that for the tie rod system to work, what happens is that an arch action develops within the masonry thickness. Here on the left-hand side, we are looking at the horizontal section, so it's a plan view of the system. You see in gray highlighted the arch that is forming within the wall. Now, for this arch to be effective, the ratio between the sag and the length and the span should be convenient. We cannot have too large span compared to the sag of the arch. And so if the transverse walls where we can provide tie rods are too far apart, usually more than 10 times the minimum thickness of the wall that we are trying to preventing from overturning, well, if that ratio is greater than 10, most likely that tying system will not be efficient. Other problems can be created by openings, by flues, which are interrupting the arch action within the wall. And in some cases, you can see here at the bottom situation, this wall, what happens is that the central pier is basically free to develop a simple overturning mechanism. It feels no restraint from the tie rods, which are provided at the edges of that diaphragm panel. So in all these cases, very slender, looking at them in the horizontal cross-section, very slender walls and the presence of openings, we may need to combine our tie rod system with a diaphragm connection and possibly strengthening and stiffening solution, so to engage the entire wall, not only its end portions. Finally, because of the arch mechanism that is developing horizontally within the thickness of the wall, we are developing also very high compressive forces in the masonry. And if our masonry is of poor quality, for example, rubble stone masonry with round stones and very, very weak mortar, in that case, the masonry may not be strong enough to resist those compressive forces, those thrusts, and simply these walls are destroying. You see full disaggregation of these walls, even though tie rods were provided, but those tie rods were completely inefficient because the material, the masonry material, was not able to withstand the forces that we're developing with this arch action. So, as I was saying, in all these cases where we cannot rely on the formation of this arch action within the wall thickness, high slenderness, openings, not so good material, we need to combine our tie rod system with a wall to diaphragm connection improvement. This can be achieved in several ways. We can basically connect the joist or the planks of our floor system, which is providing the horizontal diaphragm action. We have to connect it to the walls. You see here on the photo on the bottom right, you see all these little black dots. They are all small anchor plates for this distributed connection system throughout the diaphragm. The top photo on the right, you can see at a corner of a diaphragm panel, you can see the additional connections provided in the two orthogonal directions. In one direction, highlighted by the yellow ellipse, we have a steel strap nailed to the joist and then anchored to the exterior of the wall. On the orthogonal direction, within the red ellipse, we have instead threaded rod, you see, with a bearing plate against the perpendicular joist, and then you see that parallel to that rod, a blocking system has been introduced so to resist basically the compressive force and avoiding to bend the joist where we have placed the bearing plate. So by doing this, we can tie our diaphragm in the two directions, and we can provide this type of connections at a convenient distance, which in one direction is usually dictated by the spacing of the joist. In the other direction, this can be freely selected by the engineer. Now, the connection of the joist and of the diaphragm in general to the walls can be either mechanical or by bond, as we have seen for tie rods. In this case, the forces anchored by each connector are smaller than those usually carried by tie rods, so it's easier to provide a bond type connection. We don't need very large development length, as opposed to tie rods, which usually are made of larger diameter bars requiring longer bond length. However, in many cases, we just anchor mechanically the joist and the diaphragm to the outside of the wall. And in this case, we may have simple bearing plates or also other solutions with some aesthetical architectural value. This was especially done in the past. Also in the past, they knew the importance of connecting walls and diaphragms together, because we can find in many cases these solutions. Sometimes, if it was not desired to see the connection from outside, then this connection was provided within the thickness of the walls, using, for example, a pin type of connection. However, also in this case, we need to be careful to make sure that our retrofit solution can actually work. First of all, we have to consider that our connectors must resist tension if they're directly preventing the overturning of a wall. However, those along the intersecting walls are resisting shear, because this out-of-plane inertia is taken by those connectors acting as ties, is transferred to the diaphragm, and then the diaphragm transfers it by shear to the perpendicular walls. However, an earthquake can attack usually in both directions. So generally, we need both ties and dowels resisting tension and resisting shear along both walls in both directions. And typically, we actually design all these connectors to be able to work as both ties in tension and dowels in shear. So even though in this figure we have ties highlighted in red and dowels in black, in reality, all connections are generally designed to provide both functions. Another consideration is that these tie and dowel forces are point forces, but they need to be distributed, they need to be introduced within the diaphragm as distributed loads. And this must be done close to the connection with the walls. Then, if we engage the diaphragm, we need to make sure that this diaphragm is strong enough to resist forces arising from its response, which is going to be like the one of a simply supported beam. You see, the diaphragm has inertia forces from its own weight and from the walls that it is restraining out of plane. Well, it is supported by the other orthogonal walls at the edges, and so it's like a simply supported beam with a uniformly distributed load subjected to bending and shear. Bending result in tension and compression forces concentrated at the, say, top and bottom on walls C2 and C1 of the diaphragm that basically constitute the so-called chords of the diaphragm. On the other hand, parallel to the excitation direction, we need to transfer shear to the parallel walls. And to do so, we may need to take advantage of the collector action along this other connection. Within collectors, we develop tension forces if the reacting wall is not continuous, but it has openings. So basically, the transfer happens only in correspondence with the piers below the diaphragm. Where there are openings, this transfer is basically not effective. So because the diaphragm transfer shear throughout the length of the wall R3, while this is transferred below only over the length of the pier, we have development of tension forces, which must be somehow resisted. And finally, the panel of the diaphragm, the central part of the diaphragm, has to resist shear forces. Now, if you're lucky, the existing diaphragm is able to resist this tension, compression, and shear forces. But in most cases, we are not that lucky. So we need to basically provide strengthening for chords and collectors and for the diaphragm. Now, this is usually done by ring beams or bands that can also help spreading the tie and dowel forces into the diaphragm. In some cases, for chords and collectors, we may take advantage of tie rods. Tie rods are post-tensioning the masonry spandrel. So this spandrel is now subjected to compression, like a pre-stressed beam, pre-stressed concrete beam, basically. So it may be able, if the post-tensioning force is properly designed, may be able to resist tensile forces without cracking, as a pre-stressed concrete beam. So we may take advantage of post-tensioning through tie rods to resist chord and collector tension forces, but in many cases, we take actually advantage of ring beams that are basically serving two roles, distributing tie and dowel forces into the diaphragm and providing tensile strength for chord and collector elements. Finally, we may need to strengthen and stiffen our diaphragm for shear. So you see, connecting the diaphragm may not be enough. If you're lucky, yes, it's enough, but in most cases, unfortunately, it ends up that the existing members cannot provide the adequate strength to effectively prevent out-of-plane overturning mechanisms. So let's start talking about ring beams or bands, which can be located inside the building. Here I'm showing two solutions. There are many, actually. The one at the top makes use of steel profiles or steel plates, can be L-shape or C-shape profiles or flat plates, which need to be connected to the diaphragm and to the wall. This solution may be associated with strengthening of the diaphragm panel. We will see in a moment different techniques to do so, or if the diaphragm strength in shear is sufficient, we may just need this ring beam, steel ring beam, connected to the existing diaphragm and to the wall. And these connections are provided by those type of dowels and ties that you've seen before, but these profiles need also to be nailed to the timber diaphragm. Another solution is with reinforced concrete tie beams. Now, this is usually a choice that goes with the strengthening of the floor diaphragm by adding a reinforced concrete topping. It's rare, almost impossible, to find a reinforced concrete ring beam built like I'm showing, built within the diaphragm without strengthening with reinforced concrete topping the diaphragm itself. And again, the ring beam, properly reinforced, will serve to resist tension forces for cord and collector action, and will also serve to basically anchor the connectors that are also embedded in the walls. And then the diaphragm strengthening system must be properly connected to the existing flooring system, as we will see in a while when talking about retrofit of the diaphragms. Now, here in the photo, I'm showing reinforced concrete ring beam with longitudinal and transverse reinforcement, but in many cases, we don't have transverse reinforcement. You see in the photo, you can recognize the steel mesh of the diaphragm topping, and close to the boundaries, you see those larger diameter bars that are just the longitudinal reinforcement of the cords and collectors of the diaphragm without the need of any transverse reinforcement. We can also locate our ring beams or our bands on the exterior of the building, basically by wrapping the building either with steel, rods, ropes, plates, as shown here at the top, or with composite materials, such as FRP or FRCM. In this case, the ring beam serves only as reinforcement for the masonry to resist tension for cord and collector action. In this case, they don't help transferring the dowel and tie forces into the diaphragm, of course, because these elements located outside are not in contact with the diaphragm itself. And then we have usually also ring beams at the top of the walls, basically supporting the roof system. There are several solutions here. Probably the one most compatible with the existing materials are reinforced masonry ring beams. They can be reinforced in steel with individual bars or small cages. They can be made in bricks, usually in brick and masonry, even above stone masonry walls, but the stiffness of brick and stone masonry is somehow compatible. And an alternative to this solution is to use instead composites to provide the reinforcement. For example, GFRP meshes embedded in the bed joint of the top layers of the masonry, so to provide longitudinal reinforcement in a different form, not using steel. Then the roof system needs to be connected to the tie beam. For example, you see here on the left-hand side this tie-down rods connecting the roof rafters to the reinforced masonry ring beam, or we also have solutions like this with dowels reaching deep into the masonry, also below the reinforced masonry ring beam. And this is to improve connection with the masonry wall to avoid sliding and other problems at the interface between the reinforced masonry beam and the existing masonry. This is especially necessary if the existing masonry is of not very good quality. Some cases it may be also necessary to improve the quality of the masonry material, at least locally around these anchorages, for example, by joint repointing, grout injection techniques, whatever is necessary to reduce the vulnerability due to the material constituents. Other solutions for roof ring beams are involving the use of steel profiles, for example, channels. And you see this solution here with a steel channel with a timber element inside the channel so that it can be easily connected to the roofing system. Or we also have small roof trusses also embedded in the thickness of the wall to serve as top ring beams. Again, it is important to connect the ring beam to the existing masonry through dowels. Again, these dowels must be deep enough to anchor effectively the ring beam to the masonry. And as before, if the masonry is of poor quality, we may need to locally strengthen it with appropriate methods. Finally, this solution was somehow abused in Italy in the past, the use of reinforced concrete ring beams. I'm saying abused because they were introduced without proper attention to the details and to possible problems induced by the strengthening method itself. The problem of reinforced concrete ring beam is that they tend to be very stiff compared to the masonry. And we need to avoid this. So we don't want to make these concrete ring beams with large sections. They should be as small as possible to avoid a differential stiffness between the beam itself and the masonry below. So this is the first problem. Second problem, again, is a problem of connection, which in the past was not sufficient. So here I'm showing on the detail on the right side, you see this combination of dowels tying the ring beam to the masonry wall, but also reinforced injection to strengthen the masonry involved in the connection region. Again, this is especially necessary if the masonry is of quality, of low quality, and may not be able to resist the forces transferred by the ring beam. The fact that the concrete ring beam is very stiff compared to the masonry, basically without any connection, may result in relative sliding, relative movement, or actually the ring beam somehow tearing the masonry below during this sliding movement and causing a collapse of the masonry below. We have observed this in the past. The thing to be very careful is to avoid this kind of details. You see, creating a ring beam by removing a portion of masonry or anchoring the ring beam or a new diaphragm with a dovetail connection. Partial removal of masonry should be avoided as much as possible, because as we remove the masonry, look at the figure at the bottom of the slide on the left. We remove the masonry from this part here. Now we are deviating our stress trajectories all towards the exterior leaf of the masonry. Now, when we add the new diaphragm or we just create the ring beam after supporting temporarily the existing diaphragm, the new diaphragm will rest on the interior leaf. All the loads coming from above that were deviated towards the exterior leaf will remain on the exterior leaf, even if we now are placing our concrete here to form the tie beam and to close the pocket. because once we deviate that flow of forces, we cannot bring it back. And this happens, it cannot be avoided when we do this kind of intervention. So what is the consequence of this? Well, when an earthquake attacks, our floor will try to move horizontally because of its inertia. It will push against the exterior leaf, which is highly stressed in compression and which is prone to buckling. And so we risk to have kind of an explosion of our masonry outwards, and you see what happens, like in this case shown here in the photo. You see that here we had see a very beam here insisting, resting only on the interior leaf, same detail, less visible here in the other floor. Well, this caused this kind of problem. So be careful, avoid this kind of intervention. Avoid to mess up with the flow of forces within the masonry. And this is what I was saying, the problem of incompatible stiffness and weak anchorage between concrete ring beams and masonry walls, especially stone masonry walls. In all these cases, starting from L'Aquila all the way to the more recent 2016, 2017 Central Italy earthquake sequence, we observed quite extensively this problem. A wall collapsed below a stiff concrete ring beam, which was poorly connected to the masonry itself. Again, a problem of quality of masonry, which may need to be locally strengthened, problem of stiffness of this concrete ring beam, which are basically behaving as a rigid body, moving above a more flexible and weaker material, which is the supporting masonry. So try to avoid this problem because this makes the intervention completely useless. And finally, let's talk quickly about diaphragm strengthening and stiffening techniques. Remember, diaphragms has to resist shear coming from the inertia of the walls restrained out of plane and of the diaphragm itself. Now, there are several techniques. Here I'm basically focusing on timber diaphragms, but some of the solutions, the ones relying on concrete topping, can be adopted also when we have existing reinforced concrete floors or say steel purlins with masonry flat arches, steel purlins with other masonry tiles. In all these cases, the intervention with concrete topping can be adopted. The other ones are appropriate for timber diaphragms, which are more common in historical construction. First solution is to add a plank layer above the existing planks. Planks nailed, of course, to the existing planks and joists. Usually these planks are provided at a 45-degree angle, so basically we can create somehow a truss mechanism within the diaphragm. Another solution is based on the addition of plywood panels nailed to the existing diaphragm and nailed among each other to provide shear continuity between adjacent panels. Then another solution again is adding a collaborating slab, so a reinforced concrete topping, usually with lightweight concrete, to avoid increasing excessively the weight of the diaphragm. By the way, sometimes above our timber flooring system, we have some loose material that serves as a leveling material for the actual floor. Well, the weight of this layer of loose material, which is basically soil, is higher than the weight of lightweight concrete. So with this intervention, with topping, which is usually say between 4 and 7, 8 centimeter thick, we may actually not increase at all the weight of the floor. So we may be able to minimize the change in inertia of the building. The topping must be properly connected by shear studs to the joist of the existing diaphragm in order to be effective, to work together with the existing diaphragm. And finally, the last solution that I'm showing here is actually adding steel plates doweled again to the existing joist and welded with each other or bolted with each other, similarly to what is done with plywood panels. And these are photos of application of these interventions. So again, additional plank layer, additional plywood layer, reinforced concrete, lightweight concrete topping, and steel plates. Another solution may be to provide cross bracing to the diaphragm with steel rods or steel cables. And this is also done for roofs, for floors. It doesn't increase the weight at all. So it increases the thickness basically for free if we look at the weight of the building. Of course, to work this kind of system requires proper connection to steel ring beams that provide themselves connection in terms of dowels and ties with the walls. And finally, let's look at what to do quickly with walls. Here we need to be careful. We need to avoid thick concrete topping. We may use a lightweight concrete collaborating slab, for example, 4 centimeters thick or so, with proper shear connectors so that it can work together with the underlying masonry. We don't want, and I will tell you in a second why, we don't want to have a very stiff concrete topping. We want to take advantage of the masonry actually, so keep it together without messing up with the flow of forces in the structure. The alternative to this is to use composite material, and for example wrapping our walls with FRP of FRCN. By doing this, we don't change the load path due to gravity. Remember that gravity loads are stabilizing for arches, for vaults, so we don't want to take them away from the vault itself. And this is what happens with thick and stiff concrete topping. We don't want to do that. We just want to help the masonry of the vaults work together and take advantage of it. The problem that we need to solve is the fact that masonry doesn't have tensile strength. Once we solve that problem and we provide tensile strength to the composite material, with composite material now I mean existing masonry and retrofit, we are done. We don't want to do anything more, because then the masonry vault, if properly tied together, will provide sufficient stiffness. The problem is that it tends to open up because it doesn't have tensile strength. So this is what we can achieve with FRP, there is a typo, and FRCN strengthening. Now, one thing that we absolutely need to avoid when we strengthen and stiffen our diaphragms is to excessively increase the weight of the diaphragm. A heavy, stiff diaphragm is not compatible with the historical masonry. And the risk is that these very heavy new members will apply to the masonry walls forces due to the lateral inertia that cannot be resisted by the walls themselves. So again, we create a problem instead of solving it. So when we need to increase the stiffness, we need to try to do this without or with a minimal change in the weight of the structure. Masonry, especially stone masonry, but generally existing masonry structures are not meant to support heavy reinforced concrete or mixed reinforced concrete hollow tile flooring systems. The result is what you see in these photos: collapse, complete collapse of floors or facades because of the forces applied by these excessively heavy elements. And this is what I was saying about bolts, avoiding excessively stiff topping. Because the masonry initially, in its pristine conditions, resists gravity forces. When we add our concrete topping, if it is too stiff, it will attract forces because it is stiffer than the masonry vault. So it will unload the masonry vault. And if we now shake the masonry vault, we may lose the bricks, except for those around shear connectors, because these bricks are not sufficiently compressed against each other anymore. Now, the forces, the compressive action, has moved towards the new concrete vault. It has basically left the existing vault unloaded. And this is completely undesirable. It can result, and it has resulted in the past, in collapse of the vaults. So it is something that also should be extremely avoided. Now, with this, I have concluded. Thank you for your attention.